I think tomorrow is Monday, December 7th, a date that will live in infamy. But, yeah, because today's the 6th. And week 2.5, and this should be video Organic25ABlake. And we left off last week with identifying functional groups in atenolol, and this was problem 2.11 from page 57, it looks like, enalapril. And so that summarized the week 2 notes. So at some point those will show up in the weekly notes. I don't know if they're already there or if I'm going to do it yet or what. Okay, from there, on Friday I didn't want to start with formal charges. I actually forgot that we've already talked about formal charges. So we jumped back to the review because the way the review is written, all the review questions at the end of the chapter go in the order of how they were presented. So well, rather than start something new on a Friday, we'll review up to what we did. So we did up to, well, it'll be in the work for you to do on the daily plans for the week. But I think we did from 2.39 up to something, 2.43. Okay, so acetylsalicylic acid, it's always hard for me to say. This is aspirin. This is the stuff that later in the year I want to turn into wintergreen oil. We made a lab for that last year. It turned out pretty good. So we'll try that again this year. It'll give us a lot of lab technique experience. It says draw all the carbon atoms, hydrogen atoms, and lone pairs for the following compounds. So that's what acetylsalicylic acid looks like. And the next one, acetaminophen, Tylenol, is kind of similar. I mean, you can actually turn one into the other. It's not a real simple thing, but we need many steps, but it can be done. So there I've got all the lone pairs and stuff included. I've got lone pairs here, here, and here. Hydrogen atoms are included. And then caffeine, my favorite one of the group, coffee drinker. Really hooked on caffeine in the morning at least. This is what it looks like. Draw bond line structures for all constitutional isomers of butane, C4H10. So it's just this and this one. And then 2.41 is draw bond line structures for all constitutional isomers of pentane. And if you go back to problem 2.4.9, it's just the same three chemicals. It's almost the same question. Then you want to turn vitamin A and vitamin C models of molecules, into bond line structures. And what's going on? 2.42. Nope, this is okay. Something is wrong. Nope, this is okay. This is vitamin A. I want to say vitamin A is ascorbic acid, and I should know that. But you can look that up and see if that's right. I remember trying to look that up, and I must have got distracted, bell must have rung or something. What a vitamin is, by the way, I'm not going to get into a lesson on vitamins, but a vitamin is an organic chemical that we need to do metabolism or some function. And we can make all of our own molecules to do everything we need to do except for a few dozen. And those molecules we pick up from somewhere else in our environment, in food, and those are vitamins. So, you know, we can't make this molecule from anything else that we've got. We have to have this molecule show up in our diet, and then we can make stuff from it. What exactly are we making? I really don't know. Maybe it's one of those things I ought to know, or once knew and forgot. Who knows? But that's what a vitamin is. It's something in our diet. It's a molecule that we have to make other stuff, and we just don't have a way to make it, so we got to get it from our food. Okay, then vitamin C looks like this. Looks like so. When its bond line structure. Number 23, how many lone pairs are found in the structure of vitamin C? Well, I added those on the next page, I think, like so. You're really not, well, you can add electron pairs on lone pairs when you have a bond line structure. It's just a little bit weird. But when you do it, you got 2, 4, 6, 8, 10, 12. Okay, going on to the next section, 2.5. Carbon atoms with formal charges. This is page 59, 2.12. For each of the compounds below, determine whether any of the nitrogen atoms bear a formal charge. There is a rule in this. You have to have lone pairs to get a formal charge, or formal charges to get lone pairs. That rule shows up here a little bit later. But here they've given you lone pairs on the first one. So once you do that, you figure out, yeah, you have a formal charge because nitrogen is in the 1, 2, 3, 4, skip the transition metals, 5th column. So it has 1, 2, 3, 4, that was a shared one, 5 electrons plus an extra shared one, which means we have an extra negative charge there. For B, apparently there's no formal charge on this. The nitrogen has 1, 2, 3, 4, 5 valence electrons available. For C, you got 1, 2, 3, 4 shared valence electrons, but not a 5th one, which means you're short one, which means you have a partial or a formal charge right there. And then D, no formal charge on this one because nitrogen has 1, 2, 3, 4, 5 with shared ones there. And the carbon are all okay. Number 2.13. For each of the compounds below, determine whether any of the oxygen atoms bear a formal charge. Okay, on the first one, they give us lone pairs here, here, and here. If you look at the periodic table, oxygen is in the 6th column. 1, 2, skip the transition, 3, 4, 5, 6, which means it keeps 6 valence electrons. It brings 6 valence electrons into the whatever molecule it's in. There's 1, 2, 3, 4, 5, 6, and a shared one. That's 7. It means you have an extra electron, so this has a formal charge of -1. B. We want to know about the oxygeners. 1, 2, 3, 4, 5. Something's wrong here. What did I do wrong on B? Yeah, it's not enough. So I should have a formal charge on there that I don't have. Where do I want to put it? Right here. On C, they give us the lone pairs. There's 1, 2, 3, 4, shared one there, that's 6, no formal charge. With D, we got the oxygen. You should know what this guy is. Have a polyatomic ion memorized for this one. It's the ingredient for a traditional acid. Of course, you might not really know that. I think we did that last spring. Remotely. Hydronium ion, and it has, oxygen's supposed to have 6 valence electrons. 1, 2, 3, 4, 5. It's short one, so it's a positive charge. Hydronium ion, H3O+. Great fun at parties, I guess. Okay, so going on to 59, and I mentioned this on 59. If you do that little reading there, you should do the reading. I'm doing this before I assign the reading, but you'll get to reading assigned before you see this. It talks about a rule here. Now, before I give you the rule, remember that in a bond line structure, the hydrogen atoms are there, just not drawn in. At first, you'll have trouble with that for the first day or so, but there's hydrogen atoms in there that fill that out, maybe saturated, but we don't show them. Other atoms we do write in. So you're showing the carbon with the sticks at the end of the sticks or at the bends. You're not showing the hydrogen. Other ones like oxygen, nitrogen, phosphorus, you're going to write those in. So a carbon atom with a formal charge, here's the rule, if you remember this part. The rule is, if you have a formal charge, the carbon atom will have 3 bonds and not 4. And it just works out that way. Let's take a look at these 3 they give you as an example. These 3 bond lines, and I don't have a bond line structure for this last example because it's CH3 and a lone pair. And here you have methyl groups here, 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 here. Might be missing hydrogen or something, but this is just going to have hydrogen. So I've got a chi there. I always draw chis when there's no response. On this one, if we put all the carbon and hydrogen in, we see that we have 1, 2, 3 valence electrons for the carbon, which means it's short one, so that's a positive formal charge there. If we have a positive formal charge there, it should be CH, so it'd have 1 for the H, 2, 3, it'd be short one. If you have a formal positive charge here, you'd have carbon with 3 of the 4 bonds, so there's 2 for the hydrogen and 1 there. If that formal charge is a negative, the way you can get that is to have hydrogen, 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 and 2 electrons here. A lone pair. Then you'll have 1, 2, 3, 4, 5, and you get a negative charge there. In every one of these cases, you got 3 bonds. So you got 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. That's the rule. If you've got a formal charge on a carbon, it's got 3 bonds. Going on, identifying lone pairs. To identify formal charges, you must know the lone pairs, or to identify the lone pairs, you must know the formal charges. Either one of those, you got to know the other one. So usually, if you've got a bond line structure, you're going to start with what the formal charge is and then figure out the lone pairs for that because they didn't draw them in. Okay, so something like this, you know, CH3, CH2, oxygen, and an extra electron, you must have 2, 4, 6, and the extra one's there, maybe. So this is what that means if you put both of them there. It's best if you have both of them. Now, then they get into a table of rules for oxygen. And I didn't want to write all these out. I suppose you should read this and look at the examples, but I think you can just work with it and be fine. Here are some examples of where oxygen has a bond in 3 lone pairs, 2 bonds and 2 lone pairs, 3 bonds, and 1 lone pair. Just remember it has to add up to 6, or if it doesn't, you're going to have a positive charge or a negative charge. So on 2.14, it says draw lone pairs on each of the oxygen atoms in the compounds. It says try to identify all lone pairs without having to count. For whatever reason, the author wants you to do that because he thinks it's quicker. I don't know. I don't see the problem with counting it. So I'm not going to do that. You're allowed to count them. Here you got 1, 2, 3, 4, 5, 6. So no formal charge. 1, 2, 3, 4, 5, 6. No formal charge. 1, 2, 3, 4, 5, 6. No formal charge. Here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Count the hydrogen bond. Or the bond to hydrogen, I should say. Here we've got 1, 2, 3, 4, 5, 6. Here we got 1, 2, 3, 4, 5, 6, 7. So I've got a formal negative charge there for D. And E has a formal negative charge, so it's 1, 2, 3, 4, 5, 6, and 7 there. Going on, and then we'll go to another another video. For F, no formal charge given. 1, 2, 3, 4, 5, 6, we're good. G has a formal charge for a positive, so that oxygen has 1, 2, 3, 4, 5. That's why it's positive, it needs 1 more. H, here's your hydronium again. 1, 2, 3, 4, 5. So oxygen still is short of valence electrons, so it's got as a positive formal charge. I. 1, 2, 3, 4, 5, 6, that one's good. 1, 2, 3, 4, 5, that's short one, so it's positive. And 1, 2, 3, 4, 5, 6, 7, that has an extra one, so it's negative. And H, I, and J. Something's wrong. F, G, H, I, this shouldn't be G, it should be J. That's confusing. Okay, the oxygen that are shown in there, we have 1, 2, 3, 4, 5. That needs to be positive because it doesn't have the 6th one. And 1, 2, 3, 4, 5, 6, that has no formal charge. It's got 6 valence electrons at its disposal. Okay. I'll do the next one and then we'll do the next table. So you got a carbene and they have that drawn and they want to know if it's got a formal charge, I think. But you have for carbon 1, 2, 3, 4, it's in the 4th column. 1, 2, 3, 4 is what you've got, so no formal charge on this one. It's got 2 electrons in bonds and 2 is a lone pair. Okay, so I'm going to wrap this up. It's Organic25ABlake, I believe. Go to the next one. Organic25B Blake.